welcome back. This is the third lecture on this series of lectures called Solving Nonlinear Equations Using Linear Algebra. My name is Daniel Cabarcas, and if you haven't seen the other ones, they will be recorded and you can go back and see those. I'm going to do a quick recap of what we did last time before we start. So we described an algorithm called Excel, the Excel algorithm, to solve a system of polynomial equations using Gaussian elimination, but this is a non-linear system of equations. And then we explain the theoretical background that makes this possible. Today, we're gonna talk about the F4 algorithm, and then we will discuss some ways to improve on these algorithms, avoiding reductions to zero. So the general idea of the Excel algorithm was to start with the system of equations, linearize the system to construct a matrix where the columns correspond to monomials, then do Gaussian elimination to echelonize the matrix. If you can solve, great. If not, you multiply by variables to get equations at a larger degree, and you get a larger system with more equations, which you can then again echelonize, and hopefully at some point you will find solutions. And then at some point you will find solutions down here at the bottom. So in this case, you get two linear equations, and this should give you the solution. Now, the reason why this worked, we showed, was because you can always, if you have a stagger, so an ideal is a vector space, and if you have a basis for a vector space, a staggered basis for a vector space, then you can read a Groebner basis from that staggered linear basis. Now, that's an infinite basis for an ideal, so you cannot do it directly. And what we do is we do it one grade at a time, 1 degree at a time. So we support ourselves on the, on the grading of the ideal to do it 1 degree at a time. So we do the same. Now we're talking about a finite dimensional vector space. We can find a staggered linear basis of that vector space, and then from there we can read a d-Groebner basis at degree d. And then it is possible to prove that at some degree, a d-Groebner basis becomes a Groebner basis for the whole idea. So all you have to do is to go to a high enough degree, and then for sure you will find a Groebner basis. We defined what a Macaulay matrix is, which is this matrix with the coefficients of the polynomials, and then we quickly explain how to do it in the homogeneous case and the non-homogeneous case. And the problem was that on every description we gave, it was not clear what was the termination condition. So when I wrote this, I said something like, while no solution is found. What do we mean by why no solution is found? How do you know that you already found a solution? So that's what we will start talking about now. How do we know how to stop? How do we know that this degree was enough to find a Groebner basis? All right. So we need a termination condition. One option is to use Buchberger's criterion. So Buchberger's criterion tells you that if for every pair of polynomials in the basis, the S polynomial reduces to 0 or gives you a 0 as the remainder of division by G, then you have a Groebner basis. So you could go to a certain degree, check every single pair, do the S polynomial, do the division algorithm, and if all of those go to 0, you're done. But that would be extremely expensive, and we would have wasted a lot of time on all those reductions of the matrices. So what was the point? So this is not really a great idea, but it's always possible. In certain cases, if we know something about the ideal or about its Groebner basis, then it is possible to decide termination more efficiently. So we need to know something more about the ideal or something about the Groebner basis. And for example, in the homogeneous zero-dimensional case, and by zero-dimensional, I mean that the dimension of the solution space is 0, which means that the number of solutions in the algebraic closure is finite. So so it's like isolated points. There's zero-dimensional space. Then in that case, at some point, at some degree, you're gonna get all the monomials. The dimension of the space at some degree is going to be the same as the dimension of the polynomial ring. So we can simply go up to the degree where we get every single monomial of that degree as a leading term. And there, you know that we're done. So that is a possible way to terminate. And it's usually, it's common to do this, and it's very useful. Even easier, if we know that the system has a unique solution, then we expect to have n linear equations at some point. The Groebner basis will contain n linear equations. And therefore, that's what we look for. We go to a degree so that at the end, we get n linear equations. So things like that, we can use certain conditions, but it's still, and there's another option. Another option is that perhaps we can estimate the degree, a suitable degree D. And this is common for generic systems. So systems that do not have a lot of structure, that are in a way generic. So for example, if you take random quadratic polynomials in n variables, we can estimate very precisely what is the degree at which it's gonna, so that you're gonna be able to solve. So things like that can be done in some cases. And that's also a way to terminate. You simply go straight directly to the degree where you know you're gonna have a solution. Now, so in the last lecture tomorrow, I will be talking about the last option. When we talk about the complexity, I will cover part of this topic, how to estimate a suitable degree D under generic conditions. And this is quite useful in cryptography. This is often what we want. We predict at what degree we're going to solve, and this is going to also give us the complexity of the algorithm because we know the size of the matrix we're going to have to solve. And today, I'm going to be talking about a way to do actually the first part in an efficient way. It's called the F4 algorithm. The F4 algorithm is an algorithm that blends the matrix way of finding a Groebner basis with the Buchberger's way to solve it. And I'm gonna do that next. I'm gonna explain the F4 algorithm and why it works. So are there any questions? All right. So here is the basic version of the F4 algorithm. This was proposed by Faugere in 99. And it's, as I said, it's an algorithm that uses kind of good ideas from the matrix version of the and from Buchberger's algorithm. Here is how it goes. So we start with a finite set of polynomials. We include all those polynomials in G. G is gonna be where we store the basis, right? Then we construct all pairs of elements from G. While that set of pairs is not empty, we're gonna choose a subset of pairs. We're gonna remove those pairs from the set of pairs, and then we're gonna construct these polynomials here, right? And we're gonna store them in L. So what are these polynomials? This is something we have seen before. This actually looks a lot like an S polynomial. It looks like a part of an S polynomial is one of the pieces of the S polynomial, right? And that's quite important because if you get all these elements, if you get this one and the one with the G, well, you can construct the S polynomial. And we'll see that what this is going to guarantee is that every S polynomial is in the span of L, right? Next, we do something called symbolic preprocessing of L and G. So we take L and we take our current basis, and what the basic symbolic preprocessing does is that it takes the polynomials in L and it looks in G for every possible polynomial that can reduce a monomial in L. So once again, said in another way, for every monomial that appears in L, it's going to try to reduce it, but it's not going to do the reduction. It's only going to look for a leading monomial in G that can reduce that monomial that is appearing in L. And it does it in a way that it covers every possible monomial in L. And every possible monomial that can be reduced, and it keeps adding and checking that every monomial that ends up in H includes a monomial that includes polynomials that can be reduced, that can reduce it. I'll go back in a moment and get to the details of the symbolic preprocessing, but just simply think of it as adding to L polynomials from G that can reduce the elements in L. Next, we compute an echelon form of H, and we call that H tilde. And then we select from H tilde the polynomials, all the polynomials such that they are not, whose leading monomial is not a leading monomial in H. So only in H tilde plus, we're gonna keep only the ones that are new leading monomials. Finally, we insert, we concatenate, we add the polynomials in H tilde plus to our basis, and we consider every single pair of elements from the new polynomials H tilde plus and the old polynomials in G. That's the F4 algorithm. Let's look at the symbolic preprocessing in detail. So this is a symbolic preprocessing. We get L, some polynomials in L, and the basis, the current basis G. We initialize H with every element in L, and then we define this variable done, which includes the leading monomials of H. So we're claiming that the leading monomials of H are done. We're done with those. We already have those. So now, while not all monomials of H are done, while not all the monomials in H are in done, we pick an element that is a monomial in H, but it's not done yet. We haven't dealt with it yet. Let's call it T. We remove T from done, and we add T to done. So we say this one is done now. And if there exists a polynomial in the basis whose leading monomial divides T, then we insert in H exactly the polynomial whose leading monomial is T. That is G times T over the leading monomial of G. This is precisely a polynomial so that its leading monomial is T. And we add it to H. Of course, when we do this, we may get new monomials. So this may be increasing, and we have to keep going and keep going, adding everything that can possibly reduce a monomial in this set H. We add to H monomials that can reduce things that are being inserted there. right? It's the symbolic preprocessing. That's the F for algorithm. Now what I'm gonna do now is I'm gonna prove that this F for algorithm works, that it computes a Groebner basis. The intuition is as follows. Every S polynomial eventually is gonna be in the span, in the linear span of H. When you row reduce the matrix, the remainder is going to be there. It's going to be in the span. When we take only those monomials, those polynomials that add new leading monomials, we are somehow including these new leading monomials. And the size of the ideal of the leading monomials generated by G is going to increase. This cannot go forever because it's an Noetherian ring. So eventually, you get a Groebner basis. All pairs are going to be considered. So it's in between doing matrices, reduction of matrices, and Buchberger algorithm. In particular, if you take B very large, this B star very large, then you're going to get a large matrix here. H and H tilde are going to be large. You're going to do row echelon from a large matrix. So it's like you're putting together many reductions of many S polynomials at the same time. All right. Any questions before I go on into proving that the F for algorithm works? All right. So a couple of observations here that are going to be useful. First one is that for any R in the linear span of H tilde, either R is 0 or the leading monomial of R is among the leading monomials of H tilde. That's not hard to believe. Because H tilde is echelonized, it has all possible leading monomials that can be obtained by linear combinations of elements in H tilde. I'm not going to prove this one. Simple linear algebra is a good exercise. I'm going to leave it there. The second observation is that for H in H tilde plus, the leading monomial of H is not in the ideal generated by the leading monomials of G. And what I mean here is if you stop before you insert H tilde plus into G, so just after line 9, if you stop here right after line 9, then this is true. Every element in H tilde plus, its leading monomial is not among the ideal generated by the leading monomials of G. Maybe that one is not so obvious, so let me prove this one. And this is going to be very important because this is what's going to guarantee that the algorithm terminates. This is what it's going to, because it means that when you get non-empty H tilde plus and you insert it into G, then the ideal generated by the leading monomials is going to expand, and this cannot go forever. So eventually it's going to finish. This is what's going to guarantee termination. So let's do it by contradiction. For a contradiction, let's suppose that the leading monomial of H belongs to the idea generated by the leading monomials. Suppose that the leading monomial H belongs to the idea generated by the leading monomials of G. Right? So then there exists an element in G whose leading monomial divides the leading monomial of H. Let me call the leading monomial of H T, so that I don't have to write Lm of H all the time. Now, note that the leading monomial of H is a monomial in H. So I'm going to write here M of H, meaning this is the set of all monomials that happen on some polynomial in H. So the leading monomial of H is one of the monomials in H, right? So it's at some point that monomial has to be considered here. It needs to go through here at some point because it was a monomial in H. when t was considered. In the symbolic preprocessing, since there was a g that divided that, whose leading monomial divided that t, then these must have been inserted or something similar to this. So that one or any other. So I'm going to say, for simplicity, that t over the leading monomial of g times g was inserted into H. But we're saying that H is in H tilde plus. And we have just said that there's an element in H whose leading monomial is the leading monomial of H. But H tilde plus is the set of all leading monomials, is the set of polynomials that precisely are not leading monomials of H, the ones that are something new, some new. So this is a contradiction. Which contradicts the definition that was the point precisely. Tilde plus includes only new leading monomials. And here we saw how the symbolic preprocessing was important because it considers every single monomial that happens in H. All right. Any questions there? All right. So now, we're going to need a different characterization of Groebner basis, just slightly different. And I'm going to introduce it very quickly without proving it, but just because it is really important to have it. So I need a definition. Here, F is a subset of the polynomial ring. And F is an element in the ideal generated by F. Cool. There are many ways to write F in terms of the polynomials in capital F. Let's suppose we have this one here, AI, TI, FI, with the A sub i's in the field and the TI's monomials and the F sub i's in the set of polynomials. And I'm even, they don't even have to be different here. These F sub i's, we can have repetitions among the F sub i's because yes, there could be several ways. Each F can appear several times, each F sub i's. So this is a standard representation with respect to capital F, if there's no cancellations happening at the highest degree. That is, if the leading monomial of Ti Fi is always less or equal to the leading monomial of F. This is true for every I. Right? So a standard representation is a way to write F in terms of the polynomials in the basis F, so that every leading monomial of Ti is less or equal to the leading monomial of F. So there's no drop in degree at the highest degree that appears in F. There is a non-zero term here whose leading monomials is exactly the leading monomial of F. So there's no cancellation happening above. This never goes above the degree of F. Not the degree, the leading monomial of F. All right. This is similar to the division algorithm, when the division algorithm gives you 0, but it's a little bit more. It gives you a little bit more. It's like saying that it's a little bit more than saying that the division algorithm is 0, because here the order of F doesn't matter. We're just talking about the existence, if this thing exists. And the characterization I was talking about for the Groebner basis is the following. A subset G of the polynomial ring is a Groebner basis for the ideal generated by G if and only if for every pair I, j of indices S G I, Gj is equal to 0, or it has a standard representation. Standard representation with respect to G. For every pair of elements in G, the S polynomial of Gij is either 0 or it has a standard representation with respect to G. Here I should have said that G is G1 through Gm or something. So again, the order doesn't matter, which is nice. We just need that there exists such representation for every S polynomial. Right. I'm not going to prove it, but I'm going to use it. What we're going to show is that the set G constructed in this way satisfies this condition, that every S polynomial is either 0 or has a standard representation with respect to G. Now, Let's keep in mind these two results. Every element in the span of H tilde either is 0 or its leading monomial is in the leading monomial of H tilde. And every AH in H tilde plus, its leading monomial is not in the ideal generated by the leading monomial of H. Now I'm gonna prove a lemma that states our loop invariant, the loop invariant of this algorithm. Or the main loop invariant in a way. The key loop invariant of our loop, of the while loop. Says the following. For f in the span of H, f has a standard representation with respect to G union H tilde plus. And again, I mean here, right before step 10 is executed, right before line 10. So after line 9 has been executed. After line 9 is executed. And before we include H tilde plus into the base. And you can already see where we're going, because if this is true, if we manage to prove this, then we notice that the S polynomials are in the span of L, and therefore in the span of H, and therefore are here, and they will have a standard representation. If we consider every single S polynomial at some point, then we get to prove the theorem. We get the condition for this, and we have a Groebner basis. So let's prove the lemma. So we have f in the span okay. We have f in the span of H. Now, H tilde is just an echelon form of H. So the span is the same. So f is also in the span of H tilde. And by the note we had here before, either f is 0 or its leading monomial is in this, its leading monomial is among the leading monomials in H tilde. But note that the leading monomials of H tilde are the leading monomials in H union those in H tilde plus. So either they are new and they are in H tilde plus, or they are old and they are in H, right? The leading monomial in H tilde is either in H or in H tilde plus. Of course, this case is trivial. So we care about when f is different from 0. So let's suppose f is different from 0. And let G be an element in H union H tilde plus such that its leading monomial divides the leading monomial of f. Actually, we get more than this because we're in the span. So here, notice that I don't have ideal anymore. What I have here is the leading monomials of H tilde are exactly the leading monomials in H union H tilde plus. So what we get here is equality. Right? We get an element in H or H tilde plus whose leading monomial is exactly the leading monomial of f. And then we can reduce it. We can produce a new polynomial, let's say f1, by canceling the leading monomials of f, reducing it with the leading monomial of g. So we can do f and subtract exactly what we need to cancel the leading monomial of f. So what is it? Is something like take the leading coefficient of f divided by the leading coefficient of g and multiply by g. And just since they have the same leading monomial, I multiply by something so that the leading monomials cancel. And then notice that what happened here. So f1 is just a linear combination, this is linear, of an element f that is in the span of H and G, which is also in the span of H, right? G is in H union H tilde plus, which is still an element in the span of H. So then F1 is in the span of H. But we also get that the leading monomial of F1 is strictly less than the leading monomial of F. We have actually reduced the leading monomial. And we can repeat the process for F1. And we can iterate this so we get now F1 and we do the same over F1 because it's again in the span of H. We can do exactly the same, iterate, and we keep reducing and reducing, but this cannot go forever because the leading monomial is reducing and the order is a well ordering, so it's going to end at some point. So at the end, we get an expression for f in terms of these g's that belong to H union H tilde plus. So we get that f is a linear combination of coefficients multiplied by elements gi I equals 1 to some s, where the a sub i's are elements in the field, and the g sub i's are elements in H union H tilde plus. Right? Now, this is a linear combination. These GIs are here. We want a standard representation with respect to G union H tilde plus. We're not quite there yet, but almost. If we observe, how are these elements in G? Or what are these GIs? So if they are in J tilde and H tilde plus, we're good, because that's what we want. We want a standard representation with respect to G union H tilde plus. But then it says here that they could be in H. But note that every element in H is of the form a monomial multiplied by a recording. Sorry. So we're recording a course. Can you please ask? I'm sorry, I have no idea. I just came here and they told me that I should teach this class here for. I'm really sorry. I have no idea. Sorry about that. So every element in H, from the way we constructed H, was coming from taking a monomial and multiplied by an element in G. Every element in H had that form. So therefore, this thing here sorry, not this. So then this thing here is a standard representation, because we have coefficients multiplied by polynomials, and polynomials are either in this form or they are directly on H tilde plus. This is a standard representation. That's this thing here is a standard representation with respect to G union H tilde plus. Okay. Okay, any questions, comments? We have our looping variant. The elements in the span of H have a standard representation with respect to G union H tilde plus. And so now we can prove that the F4 algorithm computes a Groebner basis. Say theorem. The F4 algorithm computes a Groebner basis of N. This in place, it's gonna be very simple. The first thing is termination. Let's make sure that the algorithm terminates. This is because of the second observation we had. If H tilde plus is not empty, then the ideal generated by the leading monomials of G is strictly contained in the ideal generated by the leading monomials of G union H tilde plus. The ideal generated by the leading monomials grows every time we insert something new to G. And since this is a Noetherian ring, this has to stabilize at some point, which means that H tilde plus has to be 0 started at some point. It must stabilize, it must stop growing. H tilde plus has to be empty at some point, and therefore G is not grow anymore, and then the base, the set B is not going to grow either, and then you can eventually go through all the pairs. So from some point, H tilde plus must be empty, and the algorithm terminates. Then for correctness, left. Let's take two elements, Fg in G out. And what I mean by G out is the final set G, the final basis G that is returned at the end. So let's take two elements in the final basis. By the way, B is updated every time, and by how it was constructed originally, considering all the pairs of G, it's safe to say that the pair was considered at some point, was part of B star at some point. And when B star is considered, when that pair was considered, the S polynomial was in the span of L, because this is precisely what you need to compute the S polynomial. And the S polynomial is a linear combination of these of two things of this form. So the S polynomial of F and G was in the span of L in that loop at that point. The span of L, but then obviously also of the span of H. The span of L, which is contained in the span of H. Now, by the lemma that I'm about to erase, that S polynomial had a standard representation with respect to G union H tilde plus at that point. By this lemma, has a standard representation with respect to G union H tilde plus for that step. Now I'm talking of the G that was at that point called G. Which is contained in G out, right? And therefore, by this theory, by the previous theory, by the characterization of the Groebner basis, then G out is a Groebner basis. By characterization basis, G out is a Groebner basis. So we take two elements, F, G, and G out. That pair had to be considered at some point. That the S polynomial is in the span of L, which is contained in the span of H. And then by the previous lemma, that S polynomial had has a standard representation with respect to G union H tilde plus at that point. And those are all included in G out. And then by the characterization of the Groebner basis, that G out is a Groebner basis. Any questions? Okay, so I'm gonna take a break. When we come back, we're gonna talk about how to avoid zero reductions. So all these algorithms have, all the algorithms we have presented so far are not very efficient in the sense that they consider many pairs that reduce to zero, or they consider many polynomials that will reduce to zero anyways. So we're going to talk about how to avoid some zero reductions. Let's come back. So it's 4:07. Let's come back in 8 minutes at 4:15. All right. Be back in 8 minutes. Just before we move on to the next topic. Any questions about the F4 algorithm? Okay. Here are some references. As I said, I'm gonna try to put the slides on the website where the video recording is gonna be. Otherwise, I'll put it on my website. And otherwise, just send me an email and I'll try to get them to you. We're going to start the third part. Which is in general about computational complexity of solving of these methods. And it's going to include 3 topics. We're going to talk about avoiding zero reductions. We're going to start that topic today. This is going to lead us later to talking about another algorithm that is called the F5 algorithm. And the reason I'm going to talk about that later is because it claims, and the reason it is important is because under certain generic conditions, it guarantees that there are no reductions to zero, that it avoids every redundancy in the system under certain conditions. And then tomorrow I'll talk about some measures of how expensive this is, and this has to do with the solving degree. As you've seen now, so we're going to keep constructing larger and larger matrices, and the complexity is going to be dominated by the Gaussian elimination on the largest matrix. That's going to be the most expensive step. So the key is to know up to what degree we have to go. That is, loosely speaking, the solving degree. And there's a lot of work trying to estimate that solving degree. And there are different ways to estimate it or to measure or to know in advance what it is going to be. And this is the key to understand the complexity of the algorithm. And finally, we will talk a bit about matrix reduction algorithms and how they, what role they play, and maybe about other ways to solve these equations. If, for instance, you have a small field, it makes sense to do something hybrid where you sort of guess part of the solution. Things like that are possible. So that last part will cover a few other topics, right? But let's start now with how to avoid zero reductions. Okay. This is almost the same as we had before. This is a definition. So given a monomial order and a set of polynomial G, and a polynomial f in the polynomial ring, we say that f reduces to 0 modulo G and will be denoted by f with an arrow to 0 with a small g up down here. If f can be written as a combination where the a sub i's are in the ring, and such that the leading monomial of f is larger or equal to the leading monomials of the a sub I, g sub i's. So this is exactly what we had before. This is the standard representation. This is a different notation for the standard representation. So, and I'm repeating it because in different texts you get different notations, and we want to make sure that we understand that they are the same or how they are different. Okay, so this is exactly as a standard representation, right? It's important to note that the order of G doesn't matter, and that's why here I put G as a set and not as a list or as tuple, because here the order doesn't matter. This is, again, a little bit stronger than saying that there's a division algorithm that leads a zero remainder. This is a bit stronger because the order here doesn't matter, and it talks about the existence of this thing. It doesn't give an algorithm way to find it, but it says that it exists. And it can be proven as the theorem that I wrote before, that this is enough to have a Groebner basis, which what I mean is if every S polynomial reduces to 0 modulo G, then G is a Groebner basis. Now, the goal here in the next few slides is going to be to give us some criteria to remove some pairs from the set of all pairs, to remove some pairs that we know in advance reduce to 0. Because if they reduce to 0 already, we don't have to do division algorithm on them. We can remove them. And this is going to be important in the algorithms because it's going to save time. And here's the first easy, simple criteria we can use. For example, if let f and g be polynomials, and let's suppose that they are relatively prime. What I mean by relatively prime is that their leading monomials do not share anything. The least common multiple between the leading monomials is the product of the leading monomials. So it's something like if you had, I don't know, x, y squared as one of the leading monomials, and z w c squared w, right? they have nothing in common. They're relatively prime. Their least common multiple is just the product. It's wx y squared c squared, right? It's the product of the two things, right? If the two polynomials have leading monomials that satisfy that, then we know for sure that the S polynomial reduces to 0 modulo those two polynomials, right? And let's prove it. For simplicity, let's assume that f and g are monic. Monic means that their leading coefficients is 1. It's a little bit simpler, but just helps us on making the proof simpler, but it's the same. The proof is not so much different. So let's assume f and g monic, and let t be the least common multiple of the leading monomials of f and g. Then the S polynomial, in this case, it's going to be t over the leading monomial of f times f minus t over the leading monomial of g times g. But this, because we're assuming that they are relatively prime, the least common multiple is just the product of the leading monomials. So this t is the product of the leading monomials, and therefore what we're multiplying here by is simply the leading monomial of g. And this is the leading monomial of f. Now, one may think at this point that this is a standard representation of the S polynomial, but it's not. Right? Here we have a polynomial times f, a polynomial times g. Is it a standard representation? No, it's not a standard representation, because precisely there's cancellation happening here. These two things have the same leading monomial, and they are going to cancel to get something smaller, of a smaller leading monomial. So no, not yet. But we can rewrite these as follows. This leading monomial, let's write it as this is like g minus the smallest part of g. So let's call it something like g underline. What I mean here, let's make a small window here, is that g underbar is just a g minus its leading monomial. So I remove the leading monomial, and what I get is the lowest part of the polynomial. So the leading monomial can be written as g minus g under bar. And the same happens with the leading monomial of f. The leading monomial of f is simply f minus f under bar. Now, here we get fgf minus fg. So those two things will cancel. This one here with this one here. And we're left with f under bar g minus g under bar f. And now I claim that this is a standard representation. Once we cancel the leading monomials, once we remove that part, this, I claim, is a standard representation. What we need is that the leading monomial the leading monomial of one of these two things coincides with the leading monomial of S. And the leading monomial of S is and the reason this happens is so that these two have different leading monomials. So they cannot be canceling at the leading monomial. The reason is that they are different. So note that the leading monomial of f under bar g is different from the leading monomial of g under bar f. The reason is because otherwise, if they would be the same, then that would mean that f and g, the leading monomials f and g are not relatively prime. They have a new common factor. They have a common factor because here, if we had equality here, we would have the leading monomial of f under bar times the leading monomial of g equals the leading monomial of g under bar times the leading monomial of f. So you would have a product of the leading monomial of g equals a product of the leading monomial of f, which is smaller than the least common multiple that we already claimed. So these two things have to be different. And therefore, this thing here is a standard representation. Is a standard representation with respect to f and g, to the set that contains f and g. Right? So that's our first criteria. And now what we're going to do here is quite useful. We're going to jump to another level of abstraction about Groebner basis. So the Buchberger criteria to decide that that you have a Groebner basis was saying that every S polynomial reduces to 0. But a more abstract way to say it is that a basis for the module of syzygies reduces to 0. And we're going to introduce that language now. And it's going to be also useful later, this language of syzygies. So let F be a finite set, in this case, a tuple of M tuple of polynomials. And we say that H, also an M tuple, is a syzygy of F if this sum is equal to 0. It's like a dot product. It's like a dot product between F and H. Simply the sum from I equals 1 to M of Fi, Hi. It's doing F1 through H1 times H1, dot, up to Fm, Hm. If that's equal to 0, this is called a syzygy of F. So F is fixed. And we're talking about combinations of those F that are 0. The set of all syzygies of F forms an Kx module, so a module over the polynomial ring. A module is kind of like a vector space, but not necessarily over a field, in this case, over a ring. And it's graded, where the grading is on the maximum of the degrees of the H sub i's, F sub i's. So it's also graded. I'm not going to be talking too much about that, but it's also useful to know that it's graded. We're interested at this point only about the leading terms. So we will denote by S of F the set of syzygies of the leading terms. So I'm not interested on syzygies of S, of F, of the polynomials, but only on the leading terms. Syzygies of the leading terms. In particular, the S polynomials are syzygies of the leading terms. How come? Yes, they are precisely what you need to cancel those leading terms. And the notation here is useful. So Sij is a tuple. So now Sij is a tuple. It's not a polynomial, it's a tuple. So in position J, this is the canonical vector. In position J, it has this term, and in position I, it has this term, minus this term. So it only has two positions that are non-zero. So it's something like this. This is important to get to make sure we understand this. So we are considering something like this. Let's suppose we have three polynomials, F1, F2, F3, and we are talking about S1, 3, for example. So S1, 3 has something in position 1 and something in position 3, and a 0 in the middle. What does it have in position 1? Well, it has the least common multiple of the leading monomials. I'm going to call it T13 over T1, and then it has minus T13, T3. It has two non-zero entries, one in position 1, one in position 3, and it's precisely what you need to cancel the leading monomials of F1 and F3, right? If we understand this as syzygy, this dot product will give you 0 with the leading monomials, with the list of leading monomials, right? So this is important to keep in mind. And then the key here is that the S polynomials, no, not the S polynomials, the S asyzygies, the Sij's, are a basis for this module of syzygies of the leading terms of F. I should prove this. Let's show, at least, let's give a sketch of a proof of why it's true that the Sij's are a basis for SF. So let T be an element in SF. So this is some syzygy of the leading terms of F. Now, because there must be happening some cancellation, and let's do this. Let's express these. Its position, let's call them T1 up to T sub M. So because there must be happening some cancellation, there must be at least two positions that cancel each other when they multiply the polynomials. So there must exist I and j different from each other, such that Ti times the leading monomial of Fi is equal to Tj times the leading monomial of Fj. There must be a pair where they do cancel, otherwise it could not be a syzygy. And then what we can do is we can design we can take an Sij and subtract it from this so that we cancel the Ti entry. Right? So I'm going to sketch the proof. So this is not exactly a proof, but we can subtract from F an appropriate factor of Sij so that the ith entry of T cancels. why is that possible? Well, look, because these two things are equal, then this must divide the least common multiple of the leading terms of Fi and Fj. And that's precisely the leading what we get in the Sij. So we can multiply by appropriate monomials these Sij subtracted from these and get what we want and get this cancelled. And the other, and when we do that, we are only affecting, so it would look something like this. T minus some something here. Let's call it, I don't know, R multiplied by Sij. Right? And we're only affecting the entries I and j, because those are the only non-zero of Sij. So when we do that, we are canceling one entry and then affecting only this other entry. So the result is a CCG, but with fewer non-zero components. This one here is again in SF and has fewer non-zero components. Maybe I leave it as a homework to express this R precisely. Use the fact that these two things are equal and that we know exactly how Sij is to precisely compute what R is, so that we cancel the ith entry. And then what we get is a new CCG in SF, but with fewer non-zero components. If you continue this, you eventually run out of entries. So iterate until you get 0. Zero, the trivial CCG. And that will give you an expression of T in terms of the Sijs. You continue doing this, subtracting, removing non-zero entries until you get there. So nice. We have a basis for the module of CCGs of the leading monomials. And why is that useful? Well, because we can restate the we have another characterization of Groebner basis that is as follows. Let G be a basis for an ideal I, and B a homogeneous basis for the module of CCGs of the leading monomials of G, of the leading terms of G. Then G is a Groebner basis if and only if for every CCG in B, the dot product of S and G reduces to 0 modulo G. So before we had that B has to be the set of S polynomials. Now we are saying you can use any homogeneous basis for the modulo of syzygies of the leading terms. I'm not going to prove this theorem, but it's kind of the same, it's in the same spirit. It's pretty much the same proof as the proof that of the first theorem that I proved about Groebner basis. But it's very powerful because from a computational point of view, we can hope to get smaller homogeneous bases for the modulo of syzygies, and therefore have to do fewer computations. And so here I'm gonna introduce a second criteria for redundant S polynomials. Okay. This one says the following: let G be the M tuple G1 through Gm, and let S be a subset of these Sij's. And let's suppose that S is a basis for the modulo of syzygies of the leading terms of G. And now let's suppose we have three indices, I, J, and K, so that the leading term of GK divides the least common multiple of the leading monomials of GI and GJ. Then, if SIK and SJK are in S, we can remove Sij. We can remove Sij from S and still get a basis. So this is telling us a way to remove Sij from the basis if it satisfies this condition. Of course, we cannot remove them all. We have to make sure that Sik and Sjk are still there, but that's good. As we'll see, the proof of this is simply expressing Sij in terms of Aik and Sjk using this condition up here. Right? So as I said, what I want is to express Sij in terms of Sik and Sjk. If I do that, then it is redundant. I don't need it. Okay. So again, I'm going to assume that everything is monic, so that things are simpler to write. So let's assume polynomials are monic. And let's give some names here so that we can write things easier. So let's call Ti the leading monomial of Gi, and Tij the least common multiple of Ti and Tj. So that Sij is simply Tij over Ti in position EI minus Tij over Tj in position EJ. Okay. Now, note, since we are assuming that the leading term of GK divides, since the leading term of GK divides the least common multiple of GI, then we know that Tik and Tjk both divide Tij, right? Because Tik is the least common multiple between Ti and Tk. Tk divides Tij, and Tj obviously also divides Tij. So Tik and Tjk divide Tij. All right. Now, with all these in place, all we need to do is some computations to try to write this in terms of this Sij in terms of the others, of Sik and Sjk. So let's see if I remember how to do this. Okay, so by definition, Sij is simply Tij over Ti in position Ei minus Tij over Tj in position Ej. And then what I'm gonna do here is I'm gonna multiply by something, add something, so that these things get canceled and I get at the end what I want, which is Tik and Tjk in the picture. So what do I have to multiply by? So I'm gonna do here, I'm gonna multiply by T, I think Ik, Tik here, and Tik here, and here. So multiply and divide by the same thing. And here, Tjk and Tjk. And multiply and divide by Tik and Tjk. And then I also need to add and subtract yes, this is good because Tik divides Tij. This is what I need. And then I'm gonna add and subtract the following. Let's get this right. Because I'm running out of time, I'm gonna do it very quickly. So let's do this Tij, Tik over Tik, Tk in position Ek, and I subtracted it, so I have to add it again, but I'm gonna write it in a different way. So here's Tik, this cancels, and now I need Tij, Tjk over Tjk, Tk in the same position, Ak. Right. And this should do it. Let's see if it works. So I'm hoping to take this one with the other one that has with this one. Let's do these two together and let's try to blend them together, to have them together so that they become SIK, right? So is this SIK? I think so. IK, and then we can take Tij as a common factor, and we can leave a Tik. So what I need is the S polynomial to happen here. So there we have Tij over something, and here we're gonna have Tik over Ti in position Ei minus Tik over Tk in position Ek, and I'm missing one factor, so this is Tij, and then we have here Ti, which is here, and so we have here Tik also. Yes, Tik. There you go. So this is okay because we know Tik divides Tij. And this is precisely SIK. And the same is going to happen when we take these two together. Okay. So we're going to get something here multiplied by Sjk. And so we had expressed in this way Sij as a combination of Sik and Sjk. And therefore, we have shown that Tij is redundant. It can be expressed as a combination of things that we already have in the basis. So we can remove it. If we find that this condition is satisfied, we can remove it. Okay. I ran out of time, so I'm going to have to leave it there. At the beginning of tomorrow, I'm going to show how to include this into a Buchberger's algorithm and also into F4 algorithm. So these ideas of removing redundant pairs in this way can be used both for the Buchberger's algorithm and for the F4 algorithm. And then we're going to talk about the F5 algorithm. And we're going to do it on a matrix version so that it gives us criteria to remove rows from the Macaulay matrix. So it's kind of a different paradigm. And then we're going to talk more about the complexity and how this removes all redundancy and so on. But let's leave it there for now. And I'll see you tomorrow. Thanks a lot for your attention. Thanks a lot. See you next time. Goodbye.